Welcome back to the deep dive. So for a while now, we've been exploring lexical scope conceptually, right? Thinking about where variables live based on, where we actually write the code.
Hmm. We use those ideas like coloring marbles, nested bubbles, trying to
Yeah.
get the foundations down.
Exactly. But today we're kind of setting those metaphors aside a bit. We're going deeper into the engine room, you could say.
That's right. We're shifting from the why and what's conceptually to the how. How does JavaScript actually handle scope?
Mhm.
And our mission today is really to dissect the scope chain.
The scope gem. Okay.
Yeah, that's the fixed hierarchy, the connections between all those nested scopes.
Mhm.
It dictates the path the engine uses to figure out where a variable actually belongs. And it always points upwards, outwards toward the global scope.
Okay, so let's start with maybe what we thought we knew from the conceptual model. We pictured like a runtime lookup, right? The code hits a variable, say students inside a loop, and it starts looking the current scope, then the next one out, and so on, until it finds it maybe way out in the global scope.
Right, that's the perfect way to think about it when you're learning. It makes sense conceptually. But here's the really cool part, and it's all about performance.
Okay.
That idea of the runtime doing the search, traveling up the chain every single time,
Yeah.
well, that's mostly not what happens.
Oh, so it's optimized somehow.
Massively optimized. The actual work of figuring out the variable's color, its originating scope, that almost always happens during the initial compilation process.
Wait, during compilation, before the code even runs?
Exactly, because lexical scope is fixed. It's determined by where you write the code, remember. It doesn't change while the program is running.
Right, okay.
So the compiler looks at your code, sees the scopes, sees the declarations, and it can figure out, okay, this reference to students here, that belongs to the global scope, RV1.
Yeah.
It basically pre-calculates the paths.
So the runtime doesn't need to search.
Nope. The compiler essentially tags the instruction. It says, when you need students, go directly to the global scope. No searching needed during execution. It just jumps straight there.
Wow, okay. That sounds like a huge performance win, especially if you're accessing a variable inside a loop that runs a million times.
It is. It avoids potentially millions of lookups. It's a core benefit of lexical scope being, well, lexical fixed at right time.
But you said almost always, so there are cases where the compiler doesn't figure it out immediately.
There is one specific edge case, yes. It happens when you reference a variable that isn't actually declared in any of the scopes lexically available within the specific file being compiled right then.
Ah, so the compiler looks locally, looks in the outer scopes within that file, finds nothing, but it can't just fail yet.
Precisely. Because that variable might be declared in a completely different script file, but share the same global scope, right? Think multiple script tags in a browser.
Okay, yeah, so it has to wait and see.
Exactly. The compiler leaves that variable reference sort of unresolved or uncolored. It defers the final decision to the runtime.
And then at runtime.
The first time the code hits that unresolved variable, the runtime does perform that scope chain lookup. It finds it probably in the shared global scope, and then it essentially caches that result.
So it only does the expensive lookup once at most.
Correct. After that first time, the engine knows exactly where it is, and subsequent accesses are just as optimized as if it had been resolved at compile time. So performance is still maintained overall.
That makes sense. And understanding that fixed compile time nature leads us nicely into shadowing.
Right.
What happens when we use the same variable name, like student name in different scopes? You've said this is completely legit.
Oh yeah, it's not just legit, it's fundamental. Shadowing is what happens when a variable declared in an inner scope has the same name as a variable in an outer scope. The inner one effectively hides or shadows the outer one.
Okay, let's walk through that example. So we have a global var student name, Susie. That's our REID1 global.
Then we write a function print student that takes a parameter, also called student name. So function print student name.
Yeah.
That parameter is, let's say, BLUE.
Perfect. Now inside that print student function, whenever the engine encounters the identifier student name,
It finds the parameter immediately.
instantly, the lookup starts in the current scope, BLU2, finds the student name parameter declaration right there, and stops. It doesn't even look further out into the RED1 global scope.
So the BLU2 parameter student name shadows the RED1 global student name.
Exactly. And this is key. Once a variable is shadowed, like the RD1 student name is here, it becomes lexically impossible to reference that outer shadowed variable from within the inner shadowing scope, BLU2, or any scopes nested inside it.
It creates like a clean boundary. Inside print student, student name only means the parameter.
Precisely. It prevents accidental modification of outer variables and keeps the inner scope clean and predictable. Okay, that makes sense for isolation, but what if I really wanted to, for some weird reason? Is there any way to, like, poke through that lexical wall and grab the global Susie from inside the function where student name means the parameter?
Ah, the forbidden knowledge.
Yeah.
Yes, there is a trick. But let me preface this heavily. This is generally considered bad practice. It's confusing, breaks expectations, and can lead to bugs. But you might see it in older code, so you need to understand how it works.
Okay. A warning noted. What's the trick?
It relies on a quirk of how the global scope interacts with the global object. In browsers, we usually call this global object window.
Window, right.
When you declare a global variable using var or declare a standard global function, JavaScript automatically creates a corresponding property on this global object window with the same name.
Oh, so if I have var student name equals Susie globally.
Then you also have a window.studentName property that basically mirrors that global variable.
So inside my function print student, even though the identifier student name refers to the parameter, I could use window.studentName to access the global one.
That's the bypass. You're not using the lexical scope lookup for window.studentName. You're doing a direct property access on the window object. And since that property acts as a sort of getter-setter for the actual global variable, voila, you've accessed Susie.
But didn't we just say shadowing is good because it provides isolation? This feels like it just punches a hole right through that.
It does. And that's why it comes with major caveats. First, this only works for accessing the global scope variable, the outermost red one. If you had, say, a green 3 scope shadowing a blue B scope variable, there's no blue scope object, that variable name trick, to access the blue U2, one from inside green 3. It's strictly a global scope thing.
Okay, only global. And what was the other limitation? Something about declaration types.
Yes, absolutely critical. This global object mirroring only happens for globals declared with var or function.
Ah.
If you declare your global variable using let, const, or class, which is generally preferred, now those do not create properties on the global object window.
So if I wrote let student name Susie, globally, the window.studentName trick wouldn't work at all.
Correct. It would likely result in undefined or an error, depending on context. This was a deliberate change in newer JavaScript versions to help keep the global object less cluttered.
Good to know. So the trick is fragile and limited. Now, one more thing related to shadowing that can cause confusion. Distinguishing between accessing the shadowed variable itself versus just copying its value.
Right. Let's say inside your function you have that parameter special that's shadowing an outer special. And you do this, var another special.
Okay, creating an object another with a property also named special.
Yeah. What you're doing is reading the value currently held by the inner parameter variable special and copying that value into the another.special property.
If special held, say, the number 42, then another dot special now also holds 42. If it held an object reference, another dot special holds a copy of that same reference.
Exactly. But the key point is, using another dot special later gives you access to that copied value. It does not give you lexical access back to the original shadowed parameter variable container itself.
So I can't use another dot special to somehow reassign the original parameter special.
No, they are distinct. Another special is an object property holding a value. Special, the parameter, is a separate variable container within the function's scope. Copying the value doesn't link them lexically.
Got it. That distinction is important. Okay, moving on. Shadowing seems straightforward, but are there rules about what can shadow what? Especially with let and var.
Yes, there are some important boundary rules. It's not a free-for-all. You can run into illegal shadowing situations.
Illegal shadowing, like it throws an error.
Exactly, a syntax error during compilation. The main conflict happens between let const, block scope, and var, function scope, when they cross paths improperly.
How so?
Okay, simple case. An inner let can always shadow an outer var, no problem there. If you have var x was 1 outside and let x2 inside, that's perfectly fine. The inner let x shadows the outer var x.
Makes sense. Inner scope wins.
But the reverse is often illegal. An inner var cannot shadow an outer let if they were in the same function scope, and the var is in an inner block relative to the let.
Whoa, okay. Give me an example of the error.
Imagine you have let special JavaScript. Maybe it's the top level of a function or just inside an outer block. Then, nested inside that block, you try to write var special equals 42.
That throws a syntax error.
Yep, instant error.
Why? What's the clash?
It comes down to hoisting again. Remember, var declarations are conceptually hoisted to the top of their enclosing function. So the compiler sees that inner var special and tries to hoist it up.
But the outer let special is already there, defining special for its block.
Exactly. The var is trying to effectively jump over or interfere with the territory already claimed by the block scope let. The let creates a boundary that the function scope var isn't allowed to just ignore or redefine within that same function context. It's a fundamental conflict in their scoping rules.
So the compiler catches this potential conflict immediately.
Hmm.
Says this block is mine, and var can't just barge in from inside.
That's a good way to put it. However, there's an important escape hatch here.
Oh.
This boundary crossing prohibition. It stops at each function boundary.
Meaning?
If you have an outer let special, and then you define a function inside that scope, and inside that function you declare var special, that is allowed.
Ah. Because the var inside the function only hoists to the top of that function, not all the way out past the let?
Precisely. The function acts like a soundproof room for the var's hoisting. So the rule recap is, inner let can always shadow outer var. Inner var can only shadow outer let if there's a function boundary separating them.
Okay, that function boundary exception is key. Got it.
Huh?
Let's switch gears slightly now and talk about functions themselves, specifically their names and scope.
Sure. So a standard function declaration, like function ask question,
Yeah.
clearly creates the identifier ask question in the scope where you declare it.
Right. And if I assign a function expression, like var ask question function, then the variable ask question is created in the outer scope.
Correct. But then there's the interesting case, the named function expression.
You mean like var ask question function of the teacher?
Exactly that. What happens there?
Well, ask question is clearly the variable in the outer scope, right?
Yes. But what about of the teacher? Where does that name live?
Can I use of the teacher outside the function?
Try it. You'll get a reference error.
Okay, so it's not in the outer scope, is it? Inside the function itself.
Bingo. The name identifier in a named function expression of the teacher in this case is created only within the function's own scope.
So inside the function, I could do console.log of the teacher.
Yes, you could. It's primarily useful for things like recursion, where the function needs a reliable way to refer to itself internally, without relying on the potentially changeable outer variable ask question.
And I remember reading that this internal name of the teacher is special somehow.
It is. It's effectively read-only. If you try to assign something else of the teacher from inside the function, especially in strict mode, you'll get a type error.
Okay, so it's a stable, internal-only, read-only identifier for the function itself.
You got it.
All right, one last function-related topic. Arrow functions. There's sometimes confusion. Do they follow different lexical scope rules?
Ah, the arrow function myth. No, they absolutely do not change the fundamental rules of lexical scope. That's a really common misconception.
So what is different about them, scope-wise?
Scope-wise, pretty much nothing that affects the scope chain or variable lookup. They are mainly a syntax, sugar thing, shorter syntax, no function keyword, sometimes implicit returns.
Okay.
They're often lexically anonymous, meaning they don't have that internal of teacher style name identifier we just talked about, though engines might infer a name for debugging. But crucially, an arrow function still creates its own inner nested scope bucket, just like a traditional function does. The rules for looking up variables inside it and how it links to outer scopes are exactly the same.
So whether I write function, the way it nests within its surrounding scope and how variable lookups work outward is identical.
Identical from a lexical scope chain perspective. The major difference with arrow functions relates to this keyword. That's a whole separate topic, not about lexical scope itself.
Gotcha. So for lexical scope, function and equal behave the same way regarding nesting and lookups.
That's the key takeaway. Don't let the syntax fool you into thinking the scope rules changed.
Wow, okay. That was definitely a deep dive into the engine's mechanics. If we had to boil this down, what are the, say, top 3 structural points to remember?
Okay, top 3. First, the scope chain is real. It's the fixed, nested structure determined at compile time. That's the map.
Right, fixed map.
Second, and this is huge, variable lookup is overwhelmingly a compile time optimization. The runtime isn't usually searching. It knows where to go. That's why lexical scope is fast.
Compile time lookup, got it.
And third, shadowing is the natural consequence. Inner variables hide outer variables of the same name, making the outer ones lexically inaccessible from inside. Clean slates, except for that quirky global window trick.
Inaccessible, unless you cheat with window.
Okay, pretty much sums up the core mechanics.
And really understanding these mechanics, moving beyond just the metaphors into how compilation and the scope chain actually work seems absolutely vital if you want to write JavaScript that's predictable, performs well, and doesn't have weird bugs.
Couldn't agree more. It's the difference between hoping your code works and knowing why it works.
So we've looked deep inside the nesting. We keep hitting this outer boundary, the global scope. We saw it has unique behavior with var and window. Makes you wonder, what other secrets or specific behaviors does that global scope hold? What happens right out there at the edges of our program?
Hmm. That's definitely the next place to explore, isn't it? What really defines that outermost environment? Something for you to dig into next.